Hello everyone. Today we're going to talk about charging. Obviously, since this is a Tesla focused channel, I'm going to talk about Tesla hardware and Tesla charging, but a lot of this applies to other vehicles as well. And also I'm specifically showing hardware that would be found on a North American car. This hardware is going to be different than on the European cars because of the connector choice difference and the inclusion of three-phase. I'm just going to concentrate on the US version. If anyone has any questions that I don't cover, feel free to ask them below. I'd also like to thank all the donors I've had lately. People are really stepping up, helping me out. Even a small amount adds up, and we'll be able to buy more parts, and I'll be able to do more teardowns. And I'll tear it down so you don't have to, and we'll both go through it together. Anyway, a lot of people will recognize this. This is the charge port door on a Model 3. It's also the same on Model Y and doesn't differ too much on the other cars. But everyone from the US will recognize this port that owns a Tesla. Tesla's invented this connector before there was solid charging standards. They wanted a connector that was small, compact, durable, and could handle both AC and DC charging. The only other connector at the time was CHAdeMO, which is a really big connector, and it doesn't support AC, only DC charging. So Tesla did the right thing at the time, although now we have, standards that are across the board, which Tesla is now adapting in Europe. But in the US, we still have this. Tesla does provide an adapter that allows you to plug in a standard J1772. That's what the Society of Automotive Engineers calls this standard for AC level 1 and 2 charging, and connect it to Tesla's system. This is just a mechanical adapter. There are no electronics in here. It's just metal and plastic, because Tesla's system is backward compatible with J1772. And let's get into that. So there's 5 pins in here. These 2 big pins, and they are big. If you look at here's what the pins look like when they're taken out of the housing. Big, heavy cables designed to support, 500 or 600 amps during DC fast charging or supercharging. So that's why they're so big. These also carry the AC charging current, which even in the older Teslas could only top off at 80 amps. So the cable is oversized for AC charging. Modern Teslas will only charge up to 48 amps. Anyway, those are the 2 big pins. We've got this 3rd pin, which is medium size. That's the ground pin. That's the same as an AC ground pin. On the charger side, it's connected to the building ground. And on the car side, this is connected to the car body. And that's a safety system to ensure that no current can flow from ground to your car body if something was to energize the car body, which could shock you. It also provides a return path for the 2 signals, which are these 2 pins. They're really small in there, and these correspond to these 2 pins on the J1772 connector. These are the proximity and the pilot, sometimes called the proximity pilot and the proximity. It's a good question. I don't know why they called it PP. Anyway, I call this proximity and pilot. And what these two pins do, this pin tells the vehicle that a charge connector has been inserted, and I'll get into how that works. And then this signal is the single control pin, and this is also the single control pin for supercharging. So let's take a look at this assembly. On the top part, we've got the door, the little Tesla logo, which you can't see, which lights up during charging. There's a motor here that opens and closes this door. There's a detent in there. That's what makes that popping noise, which allows you to kind of overcome the gear train in there without breaking anything. There's also a position sensor in there, so the charge port ECU knows what the position of this door. Underneath here is another circuit board. This contains the LED, the RGB LED for lighting up the Tesla logo, and also contains an inductive sensor, which allows this board to sense the position of this door really accurately. So when you press on the door, it can sense that you're pressing on the door and open the charge port for you. And that's really all that's in there. And this is connected all to this charge port ECU, which is found right next to this in the trunk. Let's unplug that. Now we've got the actual charge port housing. This thing is really tough. It's fiber reinforced plastic. It's bolted into the body in 3 strong places with 3 large bolts. This is designed to, survive the heavy cables, and if someone were to pull or yank or trip on a cable, whatever, to not hurt any of this stuff. And then down here we have an actuator, and I don't know if you can see. Let me zoom in a little bit. There you go. So inside the connector, there's a little actuator, see? It goes up, locks, and down to unlock. And that's what locks the connector into the port. Obviously that's done for security, but it also ensures that you can't yank the cable out while it's under load. Because if you did that, especially under supercharging currents, there could be an arc explosion here. So it would be really bad. So when you press the button on the charge handle, you change the resistance of the proximity pin that tells the car you want to stop charging. It shuts down the charger, and then when the current is not flowing, it releases the connector so you can unplug it. And this thing's really awkward. There's a long cable going off the other end of the bench, but all we have here is 2 temperature sensors that sense the pins in there to monitor that they're not getting too hot. We have the connections to the proximity and pilot here and the ground, and then this cable goes to the actuator motor here. And that's really all that's in that. It goes back to the charge port ECU. Sorry, I was zoomed in still. Let me try that again. So yeah, this is the actuator cable for that, temperature sensors, and then this is the proximity and pilot pins. Goes to this connector, which plugs into charge port ECU. Let me get this chonker off the bench without destroying anything. This is the charge port ECU that would be found in the current cars, also in the Plaid. You can see that in this housing, the circuit board's much smaller because they've optimized this design over time. The original design filled the whole housing, had a lot more parts in it. It also had less capability, but let me get to that in a minute. Inside here is another automotive grade PowerPC microcontroller. This one's made by ST. It's called the SPC5 series. We have some power supply stuff. We also have this relay, and the relay enables this to switch from Supercharging Protocol to standard J1772 protocol, and I'll explain that in a minute. The other thing that's in here is this coupling transformer and this Qualcomm chip, and this is a power line communications chip, and it enables the CCS protocol. So obviously in Europe, where this is the same hardware used in Europe, that's used with a different connector to implement the CCS protocol, which is an extension of the J1772 that adds high current DC charging. The complexity of that protocol is, well, let's just say you can tell it was designed by a committee because it's incredibly complex. There's many layers, and they chose to use power line communications over the pilot line to control the signaling. It doesn't go over the DC or the AC. It's using the same line for pilot, which we'll get into. Anyway, that's really all there is on this. Yeah, the older board had a lot more parts, a smaller microcontroller because it didn't have to handle CCS. And a lot of people are wondering, why do we have this power line communications in the US when we don't have a CCS compatible port? That's because now Tesla, all they have to do is basically build a pretty simple mechanical adapter, and they already have the electronics needed for CCS. And I believe they're rolling this out in Korea now. We'll probably eventually see it in the US, but that will only work with cars built, I think, since sometime in late 2019, maybe early 2020, when they switched to the the updated ECU that has the power line communications capability. It would be possible to retrofit this, but you know, it will cost money. So let's go over some basics of how the charging works. So as I told you, there's two signals. There's the proximity and the pilot. Here's what's going on for the proximity. It's generally all passive. So inside the handle, there's just a switch that's connected to the handle. Let me see if I got one. When you move this, which releases the connection, you're also tripping that switch. So that's affecting the proximity pin. And it basically just changes the resistance from 330 to 150, or sorry, I guess it's about 480 ohms to 150 ohms. And this goes back into the EV to tell the EV that you're pressing this button, or more importantly, that the latch hasn't been made. Because it's really important that when you connect this, you can see that latch. Now it drops into place, and that releases the proximity signal, so the car knows it's safe to draw high current. Because you could have the connector just barely in, and now the high current pins aren't making good connection, which could cause a fire. So this ensures there's no way to have this connected unless it's fully latched before it'll let charging occur. And likewise, when you press the button, that tells the vehicle that you're wanting to interrupt charging, and immediately the current falls to zero. So if you yank it out, there's no arcing. It's a little different than Tesla's system, where the vehicle controls the latch rather than the person. But of course, that has to work with supercharging, which is way more risky if someone were to yank out a connector. So yeah, basically they use a divider to determine a voltage that goes into the charge port ECU and tells it whether something's connected or whether you're requesting disconnection, etc. The other pin, that's be this pin on the Tesla side, or this pin on the J side, is the pilot signal. And this is a little more complicated, but it's still pretty basic. Basically, it applies a 12 volts square wave signal. It goes from positive 12 volts to negative 12 volts, so it's actually a 24 volt signal, but only 12 volts over ground and negative 12 volts underground, using the body ground as the reference. And this is a 1 kilohertz square wave, and basically the duty cycle, which is the on time versus the off time, tells the EVSE, which is the wall side of the charger, how much current to draw. And by controlling that duty cycle, you can get anywhere from 6 to 80 amp capability. And Tesla also adds on to this a little bit. If the duty cycle goes below 10%, and Tesla sends 5% on the supercharger, that's the supercharger telling the vehicle that, hey, I want to talk digitally. And then that relay, which I showed you in the charge port ECU, throws, and then it connects a CAN transceiver, which is controller network, to that pin, and they send a 33 kilobit signal back and forth with serial data, and that communicates to the supercharger. And basically, the supercharger is effectively a dumb device. It follows instructions given by the vehicle battery management system. So only the battery management system knows how much current the battery can take at any given time. So it just sends those basically status messages to the supercharger, and then the supercharger delivers what it can according to what the vehicle says it'll accept. Obviously, depending on how the vehicle loads the signal, controls the states, and they're pretty straightforward. If you don't have one connected, there's no load, so the pilot signal stays at its 12 volts. When you first connect the EV, there's a resistor that places a load on this so that it drops down to 9 volts and tells it it's ready to charge. And then when the EV is actually ready to accept the AC, it pulls it down even further, and that lets the relay close, or contactor close, in the charger. And I can show you one of those. This is basically a simple level 1 charger that plugs into the wall. And what we have here is the power comes in, and there's a big relay here that connects the AC to the two pins on the vehicle side, but only when that pilot signal has been pulled down from 9 volts to 6 volts. And then the EVSE is telling the vehicle, based on this duty cycle, how much current it can draw. In this case, this would be like 12 amps. You can't, if you pulled more than that, you'd trip the breaker that this is connected to. So that duty cycle mechanism provides a way for the wall to let the vehicle know how much it can draw, and then the vehicle obeys that. And there's some other things like built into the standard. Back when EVs had lead acid batteries, there's a state D which tells the vehicle tells the charger that ventilation is required, and then if ventilation isn't available, it can deny the charge. And then there's an error state, but that's basically it. We talked about the duty cycle. Okay. This just shows what it would look like on an oscilloscope for the various states. And by the way, all this came from my friends over at OpenEVSE who put all this together. They have I guess I'm getting sidetracked here, but they developed a simple circuit and software this is an older version, for building your own, basically, EVSE. And this is everything you need besides the handle to implement a safe EVSE that charges. It's got the relay, there's a microcontroller in there, there's a power supply, and this is the ground fault detection that's required by the standard. Basically, all the same stuff that's implemented here. We've got the logic, the microcontroller, the power supply, and there's the ground fault detection. Not a whole lot to these. They're basically really simple devices. The Tesla's newer ones are a little smarter. They can communicate by using an extension of the Supercharger Protocol. By taking that duty cycle down to 5%, they start the CAN communication, and then they can do more complicated things communicating with the EVSE, and even get their firmware updates from the car if need be. So in the car side, this isn't exactly what's used, but there's two of these big contactors, and a contactor is a relay. It's basically a motorized switch is the simplest explanation. A small 12-volt current goes in here and then closes this big connection here. There's two of these that allow inside the car that allow the pack to directly connect to these two high current terminals. And once the supercharging protocol has been negotiated and it passes all the safety checks, the supercharger basically brings its voltage up to match the pack voltage. And then when the car sees that it's about the same, it closes these contactors. That way there's no explosion or arcing across the terminals in here. And then the supercharger just begins pushing DC directly into the car. And the early superchargers were literally just a stack of like 12 of the same charger modules that were present in the vehicle. So they're taking AC voltage from the grid and just 10 times what you could do at home. Now, obviously, they're bespoke hardware, but so they basically remoted a much bigger charger module that's sitting in a cabinet at the supercharger site, so you're not carrying around all the time. But yeah, these ensure that they basically switch the mode from DC to AC, or I should say AC to DC. And that's how charging works. What else? Yeah, the differences in Europe are mainly in the connector style. Obviously, we use three-phase in Europe. So the connector has, 3 AC pins and ground. And that enables, because it's very common for even residential sites in the EU to have three-phase. So the car is set up for that. And they also are now adhering to the standard in Europe so that it's directly compatible with CCS. In the US, not the same, but this stays the same. We still have the same power line modem for doing CCS. Guess that's about it. I think I've covered most of the basics of charging. Obviously, I'm not going to drill down into the weeds here. If people are interested, you can obviously do research online. Most of the stuff is public knowledge. There was a big commotion a while ago that Tesla's onboard charger was capable of vehicle to grid, and I have another video, actually 2 videos, where I debunk that. The onboard charger can only work one direction. It cannot export power. It wouldn't take much engineering to allow that, but Tesla didn't build it that way because Tesla has no intention of doing vehicle to grid. They want you to buy a power wall. That's how you do grid storage on a Tesla. Anyway, some EVs can do vehicle to grid where the onboard charger reverses its flow and basically takes DC from the pack and makes AC. They can either push back into the grid or run your house in the event of a blackout, something like that. But the hardware in all Teslas is not capable of that at this time. So the only possible way to get power out of a Tesla would be to use an external inverter, and then it would obviously have to have the cooperation of Tesla to allow the supercharger contactors to close when you're not supercharging, and basically export DC out of the port to an external inverter. But, even to do, 3 kilowatts, you're looking at, $500 in power electronics minimum, and it's going to be bulky and probably, have a big fan and all that. It's not going to be easy or cheap to do. So don't expect it anytime soon. I guess that's about it on charging. Again, if you have any questions, leave them below. If you would like to make a donation, I have a PayPal link in the description. And I guess that's it for now. Everyone, have a good day.